Hey there, everyone. My name is Ryan Schul. Welcome to my channel. I talk about all kinds of subjects related to data science, machine learning, artificial intelligence, deep learning, financial matters, and so on and so forth. So today I have a really cool lecture for you. It is all about analyzing New York City energy costs and energy consumption. Okay, so I found some very interesting data on the internet that I started to analyze a couple of days ago, and my findings are very interesting. I came to a conclusion which completely makes sense and I think is plausible and reasonable, and you'll see why at the end. So hopefully you can hang out for the whole session here and make it from the beginning point, which is right now, right to the very end of this, which I promise I'm not going to drag it on. Some of the videos, honestly, like went on for close to an hour. One actually went over an hour. I'm not going to subject you to that kind of treatment on a regular basis. Maybe never again. That one was a very long video, but I'm going to try to keep it very short and crisp and right to the point. Okay, so why should we even be interested in analyzing New York City energy consumption and related energy costs, or for any city, for any major metropolitan area? There's several reasons why we might want to undertake this kind of analysis, right? If we can identify high energy consumption areas based on zip codes or density, residential patterns, or energy consumption patterns, we can better understand how people use energy, try to understand the potential effects on global warming, understand how people spend money on energy, maybe reduce the cost of energy or just use more energy more efficient, right? So we're going to look at a few different topics today and try to attack this problem from different angles. We're going to look at the building types and which buildings use more energy and which use less. We're going to look at multifamily housing versus commercial versus things like libraries and police stations, fire stations, so on and so forth. We're going to try to understand the overarching socioeconomic factors, right? How that influences people's sociology or interactions with other people. We're going to try to understand seasonal patterns and variations and try to have a better appreciation for peak demand and how we manage that demand effectively, right? We're going to look at some possible renewable energy and electrification potential alternates to traditional energy. I mean, we just touched on it just a tad. It's not really, this lesson is not about that, but renewables are a viable alternative to dirty energy, which is basically oil, nuclear, is actually considered clean, believe it or not. The cleans are nuclear, hydro, wind, and solar. Nuclear is actually considered clean, but the dirty energies are coal, oil, burn oil, things like this. So if you can manage these resources better, it can lower our carbon footprint, right? And possibly reduce our energy costs overall, right? So we're going to take a quick look at renewables and just have a better understanding for energy efficiency and any compliance requirements that go along with that, right? So I'm not going to actually run this data because it takes quite a while to do the analysis. 30, maybe 40 minutes, maybe even longer. So I don't have a super powerful computer here. I'm not doing this on the cloud. I wish I had access to this stuff, but I simply don't. I do all the analysis on my laptop, so that is kind of a constraint here, and I don't have tons and tons of resources. So for me to do comprehensive analysis would take quite a while. I did it earlier in the day, and that's it. I'm just going to preserve what I had. I'm not going to rerun these in real time. So normally I would click on the cell, hit Control Enter to refresh the cell, and you would see all the updates coming live. But it's actually so slow. I don't think that's a good use of time. So we're going to avoid that technique. But I will share all the code with you, like all my videos. Once I post a video, I'll share all the source code so you have that available to you, and you can do the analysis at your leisure, okay? So when you have some free time, you can go ahead and do the same analysis I'm doing here. You'll have the same exact code. So everything should be tip-top shape for that, okay? So let's look at the first assumptions here. Winter and summer, we have somewhat of a peak. I'm multiplying the normal factor by 1.15 in the winter and 1.2 in the summer. So in the summer, we use more AC. In the winter, it's more heat. In the spring and fall, it's more mild, at least in the region where I live. I'm in New York City, so I'm putting a small damper here in the spring and curtailing the energy usage and related energy spend in the fall. But then there's going to be a slight uptick in the summer and the winter, okay? And I have all my notes here explaining why. So if you live anywhere around New York City or Northeast United States, you would understand that. Pacific Northwest probably has similar weather patterns, maybe a little bit more rainy, maybe not as quite as dramatic weather fluctuations or temperature fluctuations. But in New York City, this analysis is literally based on New York City, right? So I think these assumptions I provided here are pretty realistic, okay? So I just have one field. I have energy. I don't have daily, monthly. I don't have weekly energy, right? So I'm dividing by 12 and then multiplying by a factor over here to get monthly, weekly divided by 52, and daily divided by 365, and multiplying by a small factor. So there's a lower and upper bound for that. That's how I'm getting these numbers here. And you can see in the data frame how everything shakes out. This data set actually comes from here. So I have this link in the bottom. Whoops, what happened there? I have this link in the bottom cell right at the end here. What I'm looking at here, this is a plot of New York City and the major energy utilizers here. So this is, if you zoom in here, you can see some pretty interesting things. So we're going to reproduce a kind of a similar map at the end here. You see this is a multifamily housing unit, year built 1947, and there's the address here. This looks like the next door neighbor, so year built was the same. Here you have a different address. This is the Lower East Side now, and construction time was just about the same. 2 years, no wait, 10 years, 12 years later, okay, so on and so forth. And you have different metrics here. So downtown, this address is Water Street when the building was built, and then this is an office building, So you have some basic information. I'm just showing you this because this was my data source. I hit download CSV, and that became this source that we're using right now, this CSV file, okay? So you can go ahead and download that. And again, if you go down to the end here, I list the resource. That's the first one here. The second one is called GeoJSON. I'll show you that really quick, and then we'll move back here. So GeoJSON comes from here. I found this online. Took a little while to do the research and to like hunt and peck around for the different data sources, but this one seems very reasonable. I had some false starts. I went down some rabbit holes and didn't accomplish too much. But finally, after a lot of searching, I found this. So you can download that from this URL. Download the GeoJSON. We'll be using that in just a minute. And then at the end here, I have a Manhattan zip code map. So you can see where all the zip codes appear in Manhattan, and then you can apply that to your final, what we call it, just final analysis. What we end up with at the end, it looks very similar to this. It's pretty much analogous to this map right here. And you will need a Google Maps API. You can just Google it. Just go to Google free Maps API, Google Maps. Everybody uses it in your car when you're driving. You have a desktop application too. That's what this is. And if you go over here to apps or APIs and service on the left, you can have your own API right here. You can get it for free. Takes almost no time. Maybe 30 seconds if you're a little bit slow, maybe 60 seconds to get the API downloaded and installed for your, or just approved, right? And then you'll hit the API endpoint from the code over here. So those are the data sources. These are my notes. This is the first data source, energy use 1900. What am I talking about? 2022 was the year, right? And this was the source right here. So you can go ahead and download that so you can follow along in the lesson plan here. And then you can see we'll have things like address, zip code, building type. So we have hotel. There's all kinds of commercial, some schools. You have things like library, fire department, police department, so on and so forth. This is the energy feature that I'm using. I'm dividing by 52 to get weekly, 12 to get monthly, and 365 to get daily. This EUI is a concentration or a, what is it called? I guess I forgot what the terminology was, but I defined it a little bit later. Let me see. EUI is some kind of concentration of energy use. Where is it over here? Sorry, let me just, I won't get too distracted here. EUI, energy unit intensity. Okay, so the per square footage of energy use. So EUI is energy use intensity, and we will use that a little bit later in the analysis too. Okay, so we have all the data. We're doing some feature enhancement or feature engineering by creating new features. We have a energy monthly, weekly, and then daily over here. And then we are filtering just for New York City zip codes, okay, you can go all over Queens and Brooklyn and Bronx and Staten Island if you want. This analysis is just focusing on Manhattan. So I'm just using the zip codes between these ranges, right? So anything between 1001 and 10282, these are New York City zip codes, okay? So I'm importing that, converting the zip code to numeric. So these come as strings. I think in this type of analysis, I think either a string or numeric is fine. I converted to numeric and it worked fine. I think either one is fine with these types of things. With latitude, longitude coordinates, and we use those a little bit later, those definitely have to be numeric. Those can't be strings or the analysis will fail. I think with a zip code, either a string or a number will work. Now, obviously, like a zip code is not a normal number, so you can't do any kind of addition or subtraction on those zip codes. That doesn't make any sense. But it's just basically a geological identifier, right? So we have the simple conversion done over here. I'm looking at the head of the data frame and showing us the relevant address, zip code, building type, okay, hotel, worship facility, so that's a church, number of floors, the energy consumption, so that's pretty important, right? And then the features that we created over here. So where are they? Monthly, weekly, and daily. Okay, and then we have another feature that we'll parse out in just a bit. This is called fuel mix. They'll tell you the percentage of the overall metric that we are using here for energy, right? Where's my energy? For energy here, and you'll see the overall percent based on oil, based on coal, based on steam. If they use that kind of thing in New York City, they don't use a lot of steam, although I think a couple buildings on the Lower East Side actually do use steam, but that's not a primary source of energy. Usually it's coal or oil, right? Love ice water. Okay, so moving on here. So continuing with the analysis, we're going to go ahead and get feature named fuel mix. So I just mentioned that just a moment ago. We have this field over here that we're going to parse out. We have fuel oil, and then the code associated with that, and then natural gas is another type of energy supply that we use, right? So this comes to us all kind of packed into one single feature right here called fuel mix. But if we unpack it, we can get details about oil 1 and oil 2, two different types of oil, presumably natural gas, electricity. So this is the source of the energy that's consumed in New York City, right? You have diesel, oil 5 or 6. So they have several differentiators for oil, and then district steam. And then when you parse it all out, that's what it looks like. So you have this is the energy concentration per square foot. This is the original energy. And then fuel, 2 and 4, natural gas, electricity, diesel, and district steam. Okay, so hopefully that makes sense. Everything is being sort of unpacked a little bit if everything is packed into one feature, and we're doing some basic feature engineering where we create new features from existing features. So this is where you would import your API key. The 2 reasons I'm not going to run this code in real time is because I would need my API key to hit this Google Maps API endpoint that I mentioned before. It goes right here, right? But I can't reveal my Google key to you guys because it's strictly personal and confidential, obviously, so I can't give you that. And again, this analysis takes way too long. If I do it in real time, it would probably take 35 to 40 minutes, maybe exceeding 40 minutes, and I don't want to chew up 40 minutes of your time. So I'm just going to step through the code. I'm doing some basic narration here. Don't worry about what this cell does, all of this stuff. You have Folium maps, pandas, data frames, GeoPy, encoders, addresses. We're converting the address to a latitude, longitude coordinate down here. And then we're assigning everything back to the original data frame. But you don't have to worry about all the details and nuances. The code will work as is, okay? I can basically guarantee you if it works for me, it'll work for you. The only issue you might have is if you try to run this and it says package not found or library not found Folium, it's giving you an indication of what the issue is. So you go to your Anaconda prompt and type pip install Folium, PIPINSTALFOLIUM, and hit enter in your Anaconda prompt. If that's your issue, if you already have Folium installed, then that's a non-issue, right? You have the library, you can utilize it. If you don't have the library, it's going to prompt you with a little tiny error down here, okay? And it tells you, okay, you don't have Folium, you have to go ahead and install Folium. Now, I'm not sure why it doesn't just do that by default. You would think if the computer is smart enough to say, okay, you don't have Folium installed, let me go ahead and install that for you. But it doesn't do that. It's not designed like that. The only reason I can think of is maybe packages have extremely similar names, and you might get the wrong one, and the name could conflict with another naming package or another name convention that you have installed in your environment, and that can cause some downstream issues. So maybe the designers of these pip packages thought a long time ago, you know what, we'll just force the people to install it if that's what they really want. We're not going to auto install it. That's the only thing I can think of. I've really looked into it that much, but that kind of makes sense. Otherwise, if the computer knows that this is missing or this or whatever, it should kind of do it by default, but it just doesn't, right? So so that's it. That's the whole setup that we're dealing with here. We're going to aggregate the columns right here and convert all of these to numeric, okay, because they actually come to us as strings. This is string, all of these are strings, so I want to convert these to numerics. So I'm going to go ahead and put all of those into a list, and if I look for that, I am going to go ahead and I'm sorry, this isn't the conversion, this is the aggregation, okay? So I can type all this out. But if you use it once, or certainly if you use it more than once, you probably want to have this in the list. You can iterate through all the items in the list. And this code right here, this simple one-liner, basically captures this logic right here, right? When you go ahead and doing the sum by zip code, when we're grouping by zip code, it's aggregating all of these columns right here. So let me just take a quick step back right here. Yeah, it's fine. It's fine. Okay, so let's move on. Let's move on. That's fine. So everything is totally fine up to this point. We do the aggregation by zip code, and then we take this long column or a whole bunch of columns like this and melt it into a long vertical data frame. That's what melting is doing right here, right? So when you say dfgroup.melt, it's basically taking an unpivot. A pivot would be a long, drawn-out, multi-column data set. An unpivoted data set would be just a few columns with lots and lots of rows. It's also called melt, or it's also called stack, right? So if you take a bunch of rows and stack them on top of each other, or melt it into a vertical column, or a few vertical columns from many multiple columns, that is the equivalent of an unpivot. Okay, if you have a wide format or a pivoted format, then everything's stretched out with lots of columns and not so many rows. Okay, so that's how we get that. So this is what I thought I saw before. This is what I'm looking at now, is actually converting all of these into numerics. So if I could do control enter or control find for column and energy columns, I'm converting every single column right here to numeric, okay? PD to numeric, so pandas to numeric, just to make sure all of these are numeric. When I ran through it the first time, I realized they're all strings or objects, and Python, a string and an object are the same thing, right? But we can't do mathematical operations on strings or on objects, so we have to convert those to actual numerics. So pandas to numeric helps us do that. So that's how we get that, okay? And then we see the final result over here. You can't tell just by looking at it, is this numeric or is this a string? We kind of can a little bit, because you would have like a decimal place. You could have 10001.0 or something if that was a string, right? So that's numeric. That's what we can tell. But these look all numeric to me. But again, to test it, really you have to look at the data type to know for sure. But I just converted there, and I just confirmed right there. So I did a quick sanity check. So these are all numeric, right? These are floats, and we want to capture a float, or we want to convert that to a float. So we have this decimal point precision right here. Otherwise, everything would be converted to an integer, right? It would be rounding down right here, 93, and no, it would round down to 58, right, and so on and so forth. But we have floats here, so it captures all the decimal points with extreme precision there, right? And certainly on the latitude, longitude, we need that kind of precision if we're looking at these these lat long coordinates. Sorry, I've had a bit of a cold here for a while, for a few months actually. It's dragging on. So we want all of these to be float numbers, okay? So let's go ahead and convert this into our first graph. So we're looking at these metrics right here from this data source. I'm sorry about that. So we have our metrics here, and we're going to convert this into a Plotly bar chart. So if you want to see basically what this looks like, you can go over here and Google this. I love these Plotly charts because they're dynamic, they're interactive. You can put the mouse over it. The details of the data underneath the mouse pop up, right? You can see here, count is 11, count is 13, count is 24, 10, and what was that again? 15, and then 8, and then you can zoom in and you can zoom out to get extreme detail on these objects too, okay? So it's pretty cool how you can interact with these Plotly charts. I like it a lot. I use these in a lot of my demos here, so take a look at that when you have some free time. So yeah, we're going to create a Plotly bar chart. Here's the data frame. The x-axis is going to be the horizontal. The y is going to be the EY. That's the concentration of energy used per square foot. And okay, without further ado, we're going to go ahead and plot that, and we get this nice little chart down here. So we can see here, this zip code 10001 has an EY of 624 or 642. Okay, this zip code 10002 has slightly less, 305. This is 64. This one's higher, right? 1336. And you can see the higher the density or the higher intensity, the bigger the number and the darker the color. So that has a higher EUI. That's darker. That is darker. That's probably the highest one. And these are muted a little bit, and these are totally different color, right? It goes from dark blue to lighter and lighter blue to light red to dark red for the very short EUI. So these basically are low energy per square foot usage, right? That's low energy per square foot, low, 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 all the dark reds, and the dark blue is high EUI per square foot. So we can, that's looking at the EUI, okay? If I go over here, we can look at the daily energy, okay? And I set this drop-down control to look at the different features in its data frame, so I can get EUI, which is, again, density per square foot. This is daily by zip code across Manhattan. This is weekly by zip code across Manhattan. So we can see it goes up to almost 4 million. If I go back to daily, that is just over 500,000, 624. Then it goes 438, right? For weekly, monthly, we are looking at 21 million. And this is gigawatts, by the way. This is gigawatts. And this is, the next is annual, okay? And 228 million for this zip code for the entire year, okay? And these are pretty relative. You can see that this zip code 10003 uses predominantly more than 10001, and 1 uses more than 10002, okay? So you have this nice interactive chart here that you can play around with, and that comes from Plotly, right? And you have these different metrics: daily, weekly, monthly energy, which is actually annual, right? And then the EY, which is the square footage concentration or per square foot utilization of energy. Okay, so that should make sense, hopefully. So here's the next data source that I'm pulling in. So that comes from over here, right? And I shared that with you guys. I showed you an example of that. That comes from here, right here, and you download the GeoJSON. I share this link with you at the bottom of the workbook here. So essentially, this is all JSON data that has to be ingested as JSON, then converted into GeoJSON. So there is a few things in this file, including, well, you can look at it right here. Zip code, it's called mod Z CTA. You have to look up what that is. I looked it up. Didn't make a whole lot of sense, but there was a reason for that. They have population estimate per zip code, and then they have the geometric figure of the zip code. So they actually have like the boundaries of each zip code, which you'll see in just a few minutes when I get over there. It actually helps you to create a chart that's very similar to this, okay? So we see all the buildings, all the footprints, the layouts of all these different longitude, latitude coordinates across New York City, including building address and so on and so forth. This view, which we're going to try to reproduce to some extent. I didn't get this kind of granular detail with my data. I couldn't find that somewhere. Like, I don't know how these guys got that, but I got to the zip code level. I just couldn't get more granular than that. But then again, yeah, like it shows you the layout, the latitude, longitude, the coordinates, and then the grid view of Manhattan, right, with a little bit more granularity than I was able to procure, but we're going to get pretty close there. You'll see in just a minute. So that basically gives us the parameters or the outline of the lat longitude coordinates mixed with the zip code for each zip all around New York City. Okay, remember we're looking at this from a zip code level. That's the goal eventually. The first pass through we don't get there, but we will with the second or third iteration. You'll see that in just a minute. So yeah, I'm going ahead and pulling in all this data. And again, the reason we get this is to get the parameters of the zip codes all around New York City, right? So it shows us like the upper bound, the left, the right, north, south, east, and west parameters for all the zip codes. That's why we pull this in, and we have to merge this with the original data frame that we had back here that has zip code. Fortunately, that's how we do the merge, right? But then it has all the other things like daily energy. Well, I converted that. That's the feature engineering. Energy, EUI, address, and so on and so forth, right? So we're merging together two data frames. Each one has relevant information. I couldn't find any one data frame that has everything, so I had to pull two from two different sources and then merge them together. And you'll see that in just a moment here. So the MOD, MOD, whatever this thing is, I can't even say what it is. Data set refers to the modified zip code. Okay, I guess mod is modified. Zip is Z, right? CTA. Who knows what CTA is? I don't know if it really matters. But this is all the zip codes around New York City and the geographical boundaries of those zip codes, right? So that's where, based on these coordinates right here, we get the geometric north, south, east, and west parameters of each zip code, so we can isolate those and then pinpoint where they are relative to all the other zip codes. So that's how that works out, okay? So scrolling down a little bit, we go ahead and do, I think we did the merge here, right? Yeah, here's the merge. So the original data frame was this right here, this guy, right? So we're pulling in this data from the source coming in as JSON. We convert that to GeoJSON so we can do the merge. The merge happens right here. This is the energy data frame. This is the GeoJSON data frame. We merge those together and we come up with this. Okay, so we have address, zip code, energy. There are the features that we broke out. Everything was packed together. We separated it into the 6 different categories that we have. Lat long coordinates, latitude, longitude. This is the zip code right here. I'm looking at both and then merged together. This is what we have. So the geometry is that right there, right? And then we have all of the features from the first data frame, the grouped by data frame, right? So this is the first GDF, comes from DF and grouped, DF grouped together, then we come up with GDF, okay? So geometric data frame, that's what that stands for. So hopefully that makes sense. So now we are going to go ahead and convert all of these metrics into gigawatt hours. Okay, this is a conversion, so I looked this up online. We had originally energy, right? We divided by 365 to get that, 52 to get that, 12 to get that. Then we multiplied by this factor to get everything into gigawatts. So we have a little conversion going back and forth. Pretty straightforward, pretty simple to do. This shows me all the building type unique counts. I don't think I need that. Let me get rid of that right there. I don't need that per se. And then we're going to go ahead and plot that geodesic data frame, GDF to GDF, geodesic data frame or geometric data frame, whatever you prefer. We have latitude and longitude, the energy in gigawatts, okay? This is annual use now, so it isn't the daily, okay, like we see over here. Where's my daily energy, weekly, monthly, okay? And we had the original energy, so we convert all of those using this simple little mathematical operation right here to get daily energy, gigawatts, weekly, monthly, and this is annual. Okay, so that's it, guys. Pretty straightforward, pretty simple. When we plot it, we have this nice little plot that shows up over here. Now, this isn't everything. I think I picked 1,000. If I search for this, 1,000, let me see. Can I find it? Yeah, so, nope. I think there's one more. Let me see. It just lists 2, right? Okay. It doesn't matter. It doesn't matter. Okay, so we have this map, which looks pretty nice. Again, it's a plotly map. It's pretty cool because you can zoom in, you can zoom out, you can see what these things are. We have an office building over here. You can tell by the, what's this called, the legend. You can tell by the legend on the side what these things are. This is an office building. This is office based on the color right here. This is a hotel. And the size of the circle represents how much energy that that unit or that object uses. So this is office building. It uses 19.9 gigawatts. This is an annual basis. Okay, so 19, almost 20 gigawatts per year. This is multifamily housing. This is multifamily housing. Multifamily. This is a hotel. Okay, this is an office. This is multifamily housing, and so on and so forth. And if you click on this, you can turn these on and off. So you see multifamily housing disappear and then reappear. And then if I go down here, we can see the same thing with office. If I click that, they disappear and then they reappear. So this is pretty cool. I kind of like it, but I wanted something a little bit more intuitive. So I went above and beyond and converted all of these zip codes based on the parameter of the north, south, east, west border of the zip code into actual zip codes. And I wanted to plot that because that represents this view a little bit more similarly than the circles do. Okay, the circles are nice, but I wanted to get something that is more representative of city blocks. And I could not find the detail where I have all of the buildings like on this block. If you zoom in, you can probably see there's going to be a couple different buildings. I know that's a Chase building. I used to work down there. Across the street, you have, looks like 3 buildings. This is one. I think that's Brown Brothers Harriman. This is Zuccotti Park. And then this is one building over here on this view right here. You can tell between Maiden Lane and Liberty Street, you have a few different buildings. So I could not get that extreme detail of the shapes of the buildings. I tried a bunch of different things. Nothing really worked out. So I settled on the GeoJSON rendering of the zip codes over here. So you have 10001 again, that zip code, and we have all these geometric figures that we can convert into zip codes and then match based on the address and the overall energy utilization and the energy cost too, to marry everything together or to merge everything together. So that's the objective here. So we're pulling in this zip code boundary GeoJSON to help us with those defined boundaries. So here we can see the GeoJSON underscore data is the data set. We have the zip code to get the location. This shows us the ID as zip code. Remember, modified something, PA is zip code, whatever that thing is. And then energy, gigawatts, it's going to be the color that we use. And then the zip code is going to be the hover name. So when you put the mouse over it, we will see the zip code pop up, right? We have the center for this lat long coordinate. I just picked something that is kind of in Midtown Manhattan to get us off to a good start, right? You can pick downtown, uptown. If you don't pick that, you don't know where the map is going to start off. It could be north, south, east, or west of the city. I put these default coordinates just to help us get off to a good start here and plot this like right in the middle of Manhattan. So we have Midtown right here. We have the different zip codes, right? So that's what Plotly is giving us. And again, I like these Plotly charts just for that fact. The mouse, when you plot over it, it shows you the detail of the zip code and then the energy used. So here's 12 gigawatts per year. This is 12.6. The colors are pretty similar. Just almost the same thing, just off a little bit. Okay, so these buildings I think are pretty efficient. Again, the darker the red, the lower the energy use. This is a little bit lower, 4.25. This is 12 gigs. Here's 33 gigs. This is high energy consumption, 84 gigawatts per year. This is 84.3, 84.8 gigawatts. We go down here a little bit. So these guys are in between, right? Not too high, not too low. These are a little bit more energy conservation, energy aware. Their energy use is lower. This one's a little bit higher. And then you go down here. This is pretty low. Not even 1 gigawatt hour used per year. So that's pretty efficient. And then down here you have 37. So this is probably a lot of park space over here or something like that. And then you have 31 gigawatts. Okay, so almost done here. Just bear with me for a couple more minutes. So we have the group by zip code, building type. I want to look at the daily energy gigawatts, weekly, monthly, and then overall energy, right? And I want to sort this. So I'm sorting in ascending equals default. So basically that's descending order with the highest to the lowest. So the highest energy use, 137 gigawatts per year. That's multifamily housing. This is the daily, weekly, and monthly, and that is zip code 10028. If we go up there, we should see that pretty easily, I think. 10028 should be like a dark red, right? 10029, 10035, 10028. Well, the neighbor seems to use a little bit more, 10021, 10028, uh, or 10029. You know what? That might be something just slightly off here. I thought it said 10028. But it might be bleeding over into this next zip code in a little bit. So it's pretty close. Um, we might want to do a little bit of investigation just to see a little bit deeper, like, um, is this 100% correct? And does it match with what we see over here? Now, on the surface, I'm saying this is realistic, this is plausible. I think it passes the validation test. I think it passes the sanity check. But you know what? I just hacked this code together in a couple days. So I didn't have a team looking at it. I do all this work by myself. I don't have anybody to work with. It's just me doing all of these demos and these teaching lessons. So I think this is pretty close. It would be good to have a second pair of eyes on this. That would be nice, but I don't have that kind of opportunity to pass this on to somebody else. I have to do it by myself or it just doesn't get done. So here we can see multifamily housing. We saw traditionally that these buildings tend to use a lot of energy. K-12 school uses less energy. That makes sense to me. Kids are gone on the weekends. They're only there 9 a.m. until like 2:30 p.m. For some reason, the schools get out at 2:30. My wife and I were talking about this today. I have no idea why. You'd think the kids would stay in there until 5 or 5:30 when the parents get home from school, but nope. They get out at 2:30 while the parents are still at work. So the kids are just there using less energy. Fire stations not going to use a lot of energy. Library won't use a whole lot. All these New York City libraries are closed on Sunday, unfortunately. So there's one full day. They're not using hardly any electricity, maybe for those exit signs that say red all the time. But beyond that, they're not using a whole lot of energy, right? So these fall into the lower end of the spectrum, and these multifamily units are on the high end, right? Let's look at EUI. So again, zip code, building type, and we are sorting this in descending orders. So I set ascending to false. So we can see the highest EUI, residential care facility, library, museum, worship facility, other restaurant, bar, and then K-12 the school. These are low per square foot. So it's a different metric, right? It's not for the whole building, it's per square foot of the building, energy consumption, right? So similar but different type of metric from the daily, weekly, monthly energy, right? And I think we are almost at the finish line. I want to look at this, again, group by zip code, and look at the total energy divided by the population. So we have total energy divided by population here. We can see which zip codes are the least efficient. 10069 is the least efficient. 1004 is close. And these are the most efficient. 10032 is 95% EUI. So again, that is energy use per square foot. I believe that's what it is. I just found out about this stuff the other day, so you can Google that. EUI energy. I think this is per square foot, and this is the most efficient. 1031 is the most efficient zip code by energy use per square foot. Okay, so that's it in a nutshell, guys. We have the NYC zip codes. We plotted everything based on the parameters of those GeoJSON files. And we see a single large apartment building can consume 5 to 10 gigawatts per year. And then, and such buildings will contain, or may contain 100, multiple hundreds of units. Like the building where I live, we have almost 400 units for the whole building. So it's quite a few residential spots for people. When you get up to 400, that's pretty large, and it can be 100 to 150 annually, and this sounds pretty reasonable, right? Based on what we saw on these resources over here. So this site, this right here, remember you get this file GeoJSON, and then this is the zip code of the whole city. You see 10002 down here, 10013, 10004. Okay, so we have 102, 1013, 1004 down here. If we go back and look at the map, this should be pretty much the same. 1002, 10013, and 10004 right at the bottom, the tip of Manhattan, right? The southern tip. So I think everything looks good. Looks like we're in good shape here. I have just a couple more notes. We can derive key insights from studying different metrics based on New York City energy consumption, predict and imagine supply and demand. That's what we're trying to do here. Impact of external factors. Can be extreme weather can have an impact on energy use. By all means, that is that is definitely something to consider, right? Cost optimization, right? How can we reduce these costs? Now we know what the costs are. The next step in this analysis will probably be cost mitigation or cost optimization, urban planning, and sustainability. How can we continue to strive to create energy efficient buildings and build a sustainable infrastructure in New York City, right? So that's something that we can do in the next step for this analysis. I didn't do that actually, but that would be the next logical step. And then climate change adaptation or adoption, just to understand what kind of potential impact large quantities of energy consumption can have on the local area, and then far-reaching consequences too. Is there collateral damage to upstate New York for burning and consuming coal and oil and dirty energy? What kind of impact is that going to have on the sparser, dense, sparser populated areas, right? New York City is very densely populated and upstate New York is very sparsely populated. So what would the impact be on those guys? That could be another step for additional analysis here. So that's it, guys. I'm going to wrap it up. Thank you so much for your time today. Hopefully you learned a thing or two here in this analysis. I definitely learned a couple things putting this stuff together. Hopefully you did too. So that's it. I'm going to save this code and post it. So check that out when you get a chance, and I will see you in the next video.